In this video, I'm going to talk to you about how to balance a reaction. We're going to start with why we balance the reaction, what our reasoning is for having to do this process. And it comes down to this conservation that you should have seen in the activity that we did at the beginning of the chapter. That when you took a piece of paper and you tore it into little pieces, it still had the same mass. And when you burnt the match, it appeared to get smaller, but we also observed some smoke and some gases that are coming off of that. So maybe that's the reason. And then when you react the Alka-Seltzer, the mass stays the same as long as it's in the bottle. But then when we open the lid and we let the gas out, suddenly suddenly the mass gets lower. Okay, what conservation is the inability to create or destroy something. So in our case, something that can't be created or destroyed is conserved. Now, we have to be careful with our words here. I say that it can't be created and it can't be destroyed. That doesn't mean that we can't lose it. You lose things like when the match is struck, we lose some of the matter from the smoke. We lose matter when we open a lid to a bottle and it hisses. That doesn't mean it doesn't exist. It means that we no longer have possession of it. So for our sake, okay, so what you would have seen in your lab is that mass is conserved. Well, the reason that mass gets conserved is that individual atoms have been conserved. We can't make atoms start existing and we can't make atoms stop existing. Okay, they can't be created, they cannot be destroyed. I can lose them sometimes, but they're still there. They still exist, and I can't make them appear or go away. Okay, so for example, and I'm going to have several examples here. Okay, if I have this reaction where hydrogen gas, which is diatomic, so it gets an H2, and oxygen gas, also diatomic, O2, is going to react to form water. Okay, we're going to get out our very favorite atomic models here. There you have it. Okay. So I have this hydrogen molecule that's composed of 2 hydrogen atoms, and I have this oxygen molecule composed of 2 oxygen atoms, and it's going to make a water molecule that looks like that. It has 2 hydrogens and 1 oxygen. Okay. Well, in order to get to this water molecule, I'm going to have to take apart these atoms. In a chemical reaction, what really happens is that the way the atoms are stuck to each other stops existing. All of the atoms come apart, okay, and then go back together in a different configuration, like this. Okay, so there's my water. But I still have this extra little piece right here, right? And it's not accounted for right here. When we do experiments, nobody has found an extra oxygen atom just hanging out over here. This oxygen atom has to go somewhere. Well, the way the reaction's written, it appears to not, that it's extra. The way we've got it written here is that this piece just kind of poofs out of existence. Well, that's what our law of conservation says cannot happen. Okay, so how do we make it happen? Well, I've got these 2 oxygen atoms stuck together, and those 2 hydrogens here are going to stick to one of them. Well, what if I had a second hydrogen molecule? Okay, could we make that work? Well, now if I take them apart and hook them here, okay, I get here, right? I've got 1 water molecule, and now I have 2 water molecules. Well, now it works, right? So the idea behind balancing a reaction is to communicate to someone looking at the reaction how many molecules of hydrogen I needed and how many molecules of oxygen I needed to make how many water molecules, so that I don't gain or lose any extra little pieces. Okay, I can't stop worrying about them and pretend like they stopped existing, because they don't. So I need the number of pieces that I put in of each atom to match the number of pieces that are going to come out. Okay, so what that's going to look like. The first thing you're going to do is start with this reaction. And I'm going to change colors because once you have this reaction here, you are not allowed to change anything about this. I can't be just like, you know what, let's just make this a 1. Okay, we can't do that. We can't just like, oh, you know what, a 2 right there would make the whole thing work. No, the only things we can change are coefficients. And you'll know from math that a coefficient is a number in front of something. So like if you have something that says 3x, that 3 that multiplies that x is a coefficient, right? So we can change how many hydrogen atoms, how many oxygen atoms. I can't change what's in a hydrogen atom. We can't just simply say, well, what if oxygen molecules were made up of just one oxygen? Well, they're not. So we can't change that. We can just talk about how many of each of these things had to have gone in to make the process work. So the first thing we're going to do, again, is change colors, draw lines under there. Okay, now, actually, we're not going to change colors. I lied. You're going to, I think the dotted line helps. You don't have to draw it. List the elements that are in on each side. So I have hydrogen on this side, and I have oxygen on this side. And I have hydrogen on this side, and I have oxygen on that side. So the first thing you're going to do is to list out the elements that are on each side of the reaction. If your lists don't match, you have already done something wrong. Go back and check what you've got here. Okay, you copied it wrong, or you wrote it wrong, or something happened. You have to have the same elements. Okay, next thing we're going to do is to count how many atoms of each element there are on each side. So currently on my reactant side, I have 2 atoms of hydrogen in this molecule. So I'm going to put a 2 here. And then I have 2 atoms of oxygen over here. So we're going to put a 2 there. Okay, on this side, I have 2 atoms of hydrogen. But there's an invisible 1 here, right? So I only have 1 atom of the oxygen. 1. Okay, at this point, if your 2 lists match, you're done. Sometimes it happens. Don't get caught up on, I have to change numbers. Sometimes it does just balance, just like it is. Okay, this one doesn't, right? My hydrogens match, but my oxygens don't. So now what we're going to do is we're going to put coefficients in. We're going to change these numbers so that we can make them match. You can only make numbers bigger. So don't, right now, what doesn't match are my oxygens. I have a 2 here and a 1 here. I can't make the 2 smaller to match the 1, so we're going to have to make the smaller number bigger to match the 2. If I want 2 atoms of oxygen, I'm going to need 2 molecules of water. Okay. Now when I do that, I'm going to come back and change how many counts I have. Now I have 2 oxygen atoms. But because I put this 2 here, I also have 2 hydrogen. I had 2 hydrogen, but now I've got 2 water molecules, which will have, right, a total of 1, 2, 3, 4 hydrogens, right? We're going to multiply. So we change this. Now my hydrogen atoms don't match, right? So we're going to put a 2 here to represent that I need 4 atoms of that hydrogen. And now my numbers match, right? I have 4 hydrogens, I have 2 oxygens, okay? And the only thing I was allowed to change are those coefficients. All right, I'm going to work 2 more examples, and I'm going to show you, I'll work the first example, and then I'm going to show you a trick that can be done with that one. Okay, I'll do it again, the trick, and then I'm going to work one more that has some tricky spots to it. Okay, so here, again, I'm going to make a dotted line, and then we're going to list our elements. I have aluminum, and I have copper, and I have nitrogen, and I have oxygen. I have the same elements over here. Whoops. Put them in the same order, even though they don't appear in the same order here, right? Put your 2 lists in the same order. Copper, nitrogen, oxygen. So currently I have 1 aluminum, and I have 1 copper. If you look here, I have 2 nitrogen atoms, right? Because I have 2 of these NO3 groups. So I will have 2 nitrogen, and then I'll have 6 oxygen over there. Okay. On this side, I have 1 aluminum and 1 copper, right? And then I have 3 nitrogen atoms and 9 oxygen atoms. Okay, first glance, this is a little intimidating and we're not really sure what we're going to do. We know we need to fix the nitrogen and the oxygen, but we're not sure quite what can do this because no single number is going to make that happen. If it helps, you remember, go through and draw these lines. Those are the only things you're allowed to change. Okay, well, I know that I'm going to need an even number of oxygen atoms, so let's start by putting a 2 right here. That's going to change my aluminum to 2. That's going to double the number of nitrogen atoms I need to 6. And it's going to double the number of oxygen to 18, right? There was 9 in each times 2. That'll give me 18. Well, now I think I can see what's going to happen here. I have 6 nitrogen here and 2 here, so I'm going to need 3 of these formula units. So now I have 3 copper, 6 nitrogen, and 18 oxygen. Okay, now let's make our aluminum and copper match. Okay, I have 1 aluminum here and 2 there, so I'll need a 2 here to fix that. And then I have 3 copper atoms here and only 1 here, so I'll need a 3 right here to fix that. Okay, now this 6 and this 18, they were really kind of a pain to calculate, and we didn't like to do that. So what we're going to do here is to solve this problem a second time, but this time, okay, I'm going to do it just a little bit different. Instead of separating, I'm going to keep the aluminum and the copper, but this time, instead of listing the nitrogen and oxygen separately, I'm just going to leave that nitrate ion together because it doesn't change. I have some nitrate ions here, I have some nitrate ions here, and they don't change what they are. So we're just going to leave them be like a group because they travel as a group. Okay, so we'll list them here, copper here, and then I have nitrate ions. Well, I have 1 aluminum, I have 1 copper, and I have 2 nitrates, right? There's 2 of this thing as a group. Here, again, 1 aluminum, 1 copper, and I have 3 nitrates on this side. Again, travel as a group. So, again, coefficients. Okay. What can we do to fix it? We have to make them bigger, just like we did before. I know I'm going to need an even number of nitrates, so I'm going to put a 2 here. Okay. That's going to change this to a 6. I had 3 in each, but I have 2, so that gives me a total of 6, which means I would need a 3 here to make this be a 6. Oops, I forgot. And I still need to fix my aluminum, and that changes my copper, right? And now I can fix the aluminum to here, to a 2, and then a 3 here. We'll fix my copper and see that it's the same answer both times. It doesn't matter which way you do it. If you're happy multiplying them all the way out like this, do that. If you like writing less and you would rather look at them as a group, you can do it this way. It doesn't matter. Okay, one more. Okay. This type of reaction, this kind that has a lot of carbon and hydrogen and oxygen, okay, can be kind of tough. You'll see there's like oxygen everywhere, and we don't have a lot of variety, but we have a lot. Your numbers are going to get a little bigger than you'd expect. So there's a special trick that we can use here that kind of makes this one easier, or at least a little more methodical. Okay, so I have 4 carbon atoms, yes, and then 10 hydrogen and currently 2 oxygen. And over here, I'm going to have 1 carbon, 2 hydrogen, and then I have 1, 2, 3 oxygen atoms because I've got them in 2 different places. Okay. Right now, this 2 to 3 in the oxygen, we could do the same process as before, but the oxygen's all over and they're going to change. So what I encourage you is when you have these carbon, hydrogen, and oxygen, and that's the only elements here, you're going to do them in this order. Balance the carbon and don't worry about changing any other numbers. And then balance the hydrogen and don't worry about changing any other numbers. And then we're going to fight with this oxygen right here. Okay, so to balance the carbon, we're going to need a 4 right here. Right? I'm going to need 4 CO2 molecules in order to get 4 carbon atoms. In order to balance the hydrogen, I need 10 hydrogen atoms. Okay, so I would need 5 times 2, will give me the 10. Now let's count oxygen atoms. In this carbon dioxide here, I have 4 times 2, so that's 8. We'll write that down here. Plus 5 here. And 8 and 5 gives me 13. Now I need to come over and put a number here. Now there is no whole number that I can multiply by 2 to get 13. So sometimes you'll be tempted, well, if I just put a 7 there, that's 14, and then we'll make it so many times worse. Right now, we know that there's no even number that's going to make this work. We really, really, really need this to be even. So what we're going to do is we're going to multiply everything except this oxygen here by 2. We're simply going to put a 2 here, and we're going to change this to 8, and we're going to change this to a 10. Okay, that's going to double this, and it's going to double that. But it's going to double everything over here. So now I have 8 and 20. Those are still balanced, right? I don't have to change anything. And a 26 here. Well, now I can do this. I'm going to need a 13 here in front of this oxygen to give me 26 oxygen atoms. So if you ever are working on this kind of thing and you come out to where you need an odd number of oxygen atoms and no number you can put here is going to work, just double the things you've got so far. Okay, and it will make that number come out nicely. Okay, good luck.